Hello all, welcome. Today we are going to look at probability, and so this is a revision of probability. I would expect you all to have done a course on probability. So we are going to look at probability from a different perspective. We are going to look at probability from the history of probability. We are going to go through the entire history of probability and see how each of the ideas have been developed through the course of history. I find it exciting and interesting. So let's start. We're going to start first with the question on motivation. Right? Why do we have to study probability? That's the first question we are trying to answer. Randomness is an essential tool to understand nature, and why do I say so? So, for, so before the start of the last century, the world was deterministic. So the world acted according to the rules of Newton's laws. That was the world we knew until what we now call as quantum theory came into prominence. So quantum theory suggests that the world is probabilistic in nature, and so therefore in some way probability is fundamental to nature. But one you can argue that quantum theory works in micro level, and then if we are studying macro level issues, do we want to learn probability? But even there, probability is very important. So you can see, for example, probability is also important in biology. Biological process are so many biological processes are modeled using probabilistic systems. For example, something like if you want to model evolution, evolution is in some sense probabilistic. There's a randomness in evolution. If you want to model this evolution, you need a probabilistic model. That's what I was trying to say. And next, another thing is that your success and failure of drugs or vaccines, etc. You need to specify them using the language of probability. Right. Similarly, if the question of whether a particular drug is effective in you, etc. These are all you have to use a probabilistic language to tell. So, with high percentage, you might have a particular disease. Or economics, if you want to model, let's say, price fluctuations, probability randomness is involved in. Insurance companies, they have to model things using assuming a probabilistic scenario, because since the world in some sense from their perspective is probabilistic, so they have always a question to them is which is the best premium to collect from people, right? A lower premium can attract more people, but something goes wrong, they will have to pay. So therefore they have to calculate the probability of a particular risk and how much that risk will cost them. So if you are a stock market analyst, you have to use probability. Computer science, one is artificial intelligence. Why do I say that probability is fundamental to AI? What is AI? Fundamentally, what is AI? AI is artificial intelligence. In some sense, you want to model a human being using a machine, and human beings, we do things in some random fashion. There is no, you can't say that I do things deterministic. If you are playing, let's say you are playing cricket, you are a batsman in cricket, you're not going to play the same shot for the same ball, right, all the time. There is a probabilistic analysis there always. You're going to judge what kind of particular ball. Is it going to be short pitch ball? Is it a Yorker, good length, etc.? You're going to think about what is the ball going to, what is the ball going to be, and you're going to judge. At each time interval, you're going to update yourself. Okay, this is going to be short pitch ball, etc. And then you're going to modify your judgment with time, and also you're going to decide on what shot to play in some probabilistic fashion. You're going to assume that okay, if I play this shot, okay, you're basically mitigating all the risk here, right? You're interested in reducing the risk of getting out. Next is in the use of cryptography. All these cryptographic protocols are probabilistic in nature. You are using an email client service, you are accessing your bank. these are all your messages are encrypted and sent, and you receive messages in an encrypted fashion. It's decrypted at the other side, and all this encryption and decryption happens because these protocols have been developed by people who have a thorough understanding of probability. Okay, so all this encryption, all these protocols involve probabilistic analysis and probabilistic tools. So in short, from a computer science perspective, or not just computer science, as we can see, in many other areas, probability is very crucial and very fundamental, and therefore it's good to have some understanding of probability. We're going to go through the history of probability now, and how did it all start? It all started from gambling. In some sense, the history of probability started in 16th century Italy. It's a guy called as Cardano. Who was Cardano? So Cardano was a mathematician. He was a gambler. He realized that, you see, okay, I'm taking a lot of, I'm doing a lot of, taking a lot of risk in gambling, etc. But I can get better. I can make more money if I analyze each of these games. Even though there's a lot of chance here in this my gambling thing, if I analyze and design my moves based on those analysis, I can get better. This is something Cardano observed, and Cardano observed that, and he used these analysis in making money. In fact, he wrote a book called as Games of Chance, which was published long after it was published long after he was dead. It was published in 1633, and that's something like 100 years after he was born. Now, what did Cardano know? So let's go through what how did he start thinking, right? So I'm going to take a set of cards. I have just 4 cards here, so you can see all A's, and so there are 4 symbols: hearts, spades, clubs, and dice. Here is the game. So I just shuffled each of these 4 cards. Now I don't know what is on the other side. So the game is the following. Okay, I have to pick the spades, the ace of spades. Now I can't see the cards, and if I pick the ace of spades, I win. If I don't pick the ace of spades, you win. Okay, so that's the thing. So I picked this, and okay, that's pure luck. So I win. Now, here is another game. I'm going to pick one of these cards. I pick this card. This is an ace of clubs, and I lose. Now, so assume this was like we are Cardano, and we are trying to analyze this game. Okay, so during that time, I don't know, this kind of card games were played, but they used to play with dice, for example, and a lot of many of the games involved games like this. So let's try to think we are Cardano, and let's see how he is analyzing it. So Cardano saw that, okay, see, here are 4 cards, and I have to pick one of these 4 cards, and if I pick one of these 4 cards, I win, and otherwise you win. Now, so Cardano thought, is this a good game? Is this a fair game for me? What is a fair game for me? Is this my winning chance and your winning chance, are they the same? And Cardano observed the following. This is what we feel, right? All of us feel that no, this is unfair to me. This game is unfair to me. Why is this unfair to me? That's what. So Cardano wanted a rational answer. Why is this unfair to me? And Cardano realized it is unfair to me because among these 4 cards, only 1 card is a win for me. On the other hand, 3 cards are a win for you. Okay, that's the crucial factor, and that's why this is bad. That's why this is unfair to me, is what Cardano observed. So Cardano said that, yeah, okay. So it all depends. So if it has to be a fair game, Cardano realized that, okay, then the number of choices for me and the number of choices for you should be the same, right? This is what is the first observation. So you should imagine that there was no probability at that time. etc. And therefore, he can't use the modern tools now. So he's trying to think from he's trying to develop his own probability. Right now, we know we know the answers and we know how to analyze these things. We know that what do we know? What is the probability of me winning? The probability of my win is 1 by 4 because I have to pick 1 out of 4 cards, and the probability of you winning is 3 by 4 cards. Right? We know this answer now. Like we saw, Cardano understood that the win in a game of chance depends on the possible number of outcomes. Let's also look at a few technical terms. The one term is usually these things are called an experiment. And when I pick a card, so this is an experiment I am conducting. Okay, and each of these cards, I can pick any of these cards. One, this is ace clubs, or an ace diamond, or hearts, or a spade. Each of this is an outcome. Okay, so ace, hearts, dice, spades, clubs is called as an outcome, and this entire all these outcomes, the set of all these outcomes, that is diamond, clubs, spades, and hearts, that is called as sample space. Okay, what all outcomes is your win? You win if the outcome is a club or a diamond or a hearts, because if I pick spade only, I win. So if it's a diamond, clubs, or a hearts, you win. So that these three outcomes you win, and this is called as an event. So any set of outcomes is called as an event. Okay, so an event is clubs, hearts, diamond. That's an event of your win. So my win event is spades. Okay, that's a set of an one element set. So that's also a set, right? So that's my event. So there are also other events like hearts and spades together. A set of hearts and spades is another event. So we said that picking a card is an experiment. So in this example we looked at, let's write down what is an outcome, the sample space, and an event. What are the outcomes of this game? So spades is a game, is an outcome. Diamond is another outcome. Hearts is another outcome. Clubs is another outcome. And spades is another outcome. Okay, so there are 4 outcomes possible. So these are the outcomes. Now, what is the sample space? Sample space is the set of all outcomes. So the sample space is diamond, hearts, clubs, and spades. So this is the sample space. So sample space is usually defined by omega. And what is an event? An event is a set of outcomes. You can say that it's a set of outcomes, or you can say that it's a subset of the sample space. What are some example events? The entire sample space is an event. Okay. Another event is the event of player 1 winning. And what is that? That's the set of spades. What is a set of player 2 winning? That's the rest of the symbols. Okay, that's another event. So the set of all outcomes which makes player 2 win is another event. It can be other events too. You can have an event of, let's say, diamond and hearts. That's another event. You can have another event with clubs and spades. So any subset of the outcome, any subset of the sample space is an event. So these notations I hope are clear to you. Let's go to next slide. So next slide is this is an exercise which I hope you will try out. This is a game of chance which was played in ancient India. So I have modified it to make it simple. And so the game is played between 2 players, and they have a 4-sided dice. So the dice is shown on the right side. You have the dice has 4 faces and it has a number, and then those numbers are 1, 3, 4, 6. Okay, and the game is played as follows. Player 1 rolls the dice. 2 also rolls the dice again. So when player 1 rolls, he rolls both the dice, and then player 2 rolls both the dice, and 2 wins if the sum of the numbers thrown by both players is divisible by 4. So you can think of it as 4 these dice thrown, and look at the sum of all the numbers which has come up. and that has to be divisible by 4, and if that happens, player 2 wins, otherwise player 1 wins. Okay, and the question is, you have to answer these questions. What is a sample space? It's a set of all possible outcomes. What is the winning event? Okay, so that is which subset of this sample space is a win for player 2, and who has a better chance of winning. So the question we were asking is, was Cardano's game fair? And let's recollect the game. So the game was player 1 picks 1 out of 4 aces. So you have the 4 symbols, and so player 1 wins if he is picking up a spades, otherwise player 2 wins. Now the question was, is this a fair game? And why did Cardano feel that it's not a fair game? It's not a fair game because I had in the given 4 outcomes, there's just one outcome which is favorable to me. On the other hand, all the 3 other outcomes is favorable to player 2. So therefore, player 1, it's not fair to player 1 is the assumption. Back to our card game. So I have 4 cards, and my winning outcome is if I pick the ace of spades. So Cardano said that this is not fair. Cardano realized this is not fair because you have 3 outcomes and I have 1 outcome. Okay. So in this situation, how is this fair? Okay, and so he said that no, it can only be fair if both have the same number of outcomes, right? So I have okay, you have the red cards, I have the black cards. If that is the case, Cardano said, yeah, maybe you can say that this is fair. Cardano said that okay, these two are fair if both people, the number of outcomes in both sides are the same. So you have two outcomes and I have 2 outcomes. Then you can say that it's fair. This is Cardano found out. But then Cardano realized the second, so there's then a second question. Now, okay, so there is an assumption here. There is a very fundamental assumption here is that the cards are fair. Only if the cards are fair, our split of 2 outcomes into red and black makes sense, right? Only if the cards are in fair, first of all, then this entire outcome is not, this itself is not good. As you can see, this is our challenge, right? So first we were saying that, first we were arguing that, see, this is fair. We can say that this king, picking these 2 things, this is a fair game. Right? This is a fair game. If I pick black and you get red, this is a fair game. But now, that fair game is based on the assumption that the cards are fair. Okay. Now, what do you mean by the cards are fair? Okay. So, if I have to now argue about cards are fair, probably you end up arguing about something about physics. You are going to say that, okay, the cards are somewhat transparent, so I can't see what is going to be what is printed on the other side. So the cards are not transparent, so I can't see what is on the other side. And the touch and feel has to be the same. Physically, they have to be the same. In no way, no matter what, I won't be able to understand what is on the other side. So that makes it fair. So that's kind of the physical meaning of fair. So this is getting into a lot of. So now the definition of fairness is now defined in terms of physics. It comes out on physics. So the question of what is a fair card or a fair die or a fair coin is again, how do we define what is a fair coin or a fair die? Okay. So there again I have to argue that when is it a fair card? A fair card is that each of the card is equally likely. That's kind of the argument. So again, now let's go back to our first question. So when is the game fair? The game is fair if the 2 outcomes are equally likely in a fair card. And what is a fair card? A fair card is something where each of the outcomes is equally likely. So now it's circularly defined. This is kind of a problem Cardano also realized. This entire definition is circular. To define which is to define the probability or likelihood of me winning, you have to first talk about a fair card or fair die, and then you have to now talk about a fair card or fair die. You have to again go back and talk about equal likelihood, the likelihood of of each of the outcomes. So this is kind of circularly defined. So the Cardano felt that if I want to say that the game is fair, I have to say that the number of outcomes which is a win for player 1 is same as the number of outcomes which is a win for player 2, and the cards have to be fair. So I have to argue, how do I say that the cards are fair? What is the meaning of cards being fair? The cards are fair means the each outcome in the card is equally likely. That's the meaning. So now we have now defined things in a circular manner. Why? What is the probability of player 1 winning? The probability of player 1 winning depends on a fair card, and a fair card is one where each outcome has equal probability. So it's kind of circularly we have defined this, and that's kind of trouble in this way to see probability. So so this is something Cardano also realized. Okay, so we will just keep this in back of our head that the definition of probability has a circular problem, and we come to the next question: how to make this a fair game? Okay, so assuming that let's start with an assumption that it's a fair card, and the original Cardano scheme, how to make this fair game. So one solution, as we all observed, is that okay, if player 1 picks either clubs or spades, then player 1 wins, otherwise player 2 wins. That's a fair game, assuming a fair card, right? Because the number of outcomes in player for win for player 1 is same as the number of outcomes for win for player 2. That's one way to make it a fair game. But there's another way to make it a fair game. Cardano proposed the following. Cardano said that see, player 1 has to bet 1 rupee and player 2 has to bet 3 rupees. So whatever if player 1 bets x rupees, player 2 has to bet 3x rupees. So that's Cardano's proposal to make this a fair game. Why is this? Why did he think that it's a fair game? We see that Cardano felt that in this game, player 1 has one choice and player to win, and player 2 has 3 choices to win, right? So therefore, player 1 is taking a bigger risk compared to player 2. Right. So Cardano said, so now I want the betting money to turn that risk upside down. So he says that okay, player 2 has to risk more money compared to player 1 to win. So now player 1 is going to bet 1 rupee in this game, and player 2 is going to bet 3 rupees. So now if player 1 loses, which has a higher chance of there's a higher chance of him to lose, but he is going to lose only 1 rupee. On the other hand, player 2 has a better chance of winning, smaller chance of losing, but he has a higher, if he loses, he is going to lose more money. He is going to lose 3 rupee. On the other hand, even if he wins, he is going to win a small amount, 1 rupee. So that's kind of the trade-off Cardano wanted to bring into this game to make this fair. So he felt that okay, so now even though the chance of winning for player 1 is less, his loss is less and his gains are higher if he wins. Okay, now we can ask this question: how do I check whether this game is a fair game or not? Right? That's where you need some ideas which were not in Cardano's hands. You need ideas like expectation, which was not developed at that time. That's going to come next. These things were formally answered by Pascal and Fermat, close to a century passed after the death of Cardano. Around 1650, so a French writer, and he asked Pascal. Pascal was a famous mathematician. You can see there's 2 pictures of Pascal and Fermat here. Person asked Pascal, I'm conducting this betting game there, and sometimes I have to stop the game without the match finishing. Okay, now how do I divide the betting money if a game of chance was stopped midway? This is something, for example, if you're a cricket fan, now you know there's a DRS. If a cricket match is stopped in between, one day international is stopped in between, what do? You have the DRS technology, the method. That's exactly, that's the kind of question which was, DRS was probably 10 years back, and now, so you can see, this is a question people have been asking for a long, long time. What do you do if a game is stopped in between? So Pascal and then Pascal and Fermat, they started writing letters to each other, not emails, but handwritten letters. They're trying to find an answer to this question. While trying to resolve this, they developed the concepts of what is called as random variable and expectations. Using this idea, how do I argue that the Cardano's betting game is fair? Let's try to solve that. So let's first write what is a sample space. So sample space is there are four outcomes possible. So I'm going to write one is clubs, spades, hearts, diamonds. So any of these card I could have picked any of these cards, right? So these are my four outcomes. So that forms my sample space. And now we are going to introduce what is called as a random variable. Now, in some sense, what is a random variable? So you can think of in experiments, for example, especially in physics experiments, you want to measure something with a high precision, or let's say the distance from Earth to some star. You want to measure the distance between two atoms. So you want precise measurements, and every time you measure, due to the uncertainties in your measuring device, etc., you might get slightly different values each time. Right? So therefore what you're measuring and what you're trying to measure and find out is what is called as a random variable. Now that's kind of a physical meaning for interpretation for a random variable, but in mathematics, a random variable is just a function. It's just a function from the outcomes to. So random variable is a function from outcomes to a real number. What are we interested in finding out in this experiment? So in this, we want to find out whether Cardano's betting game is fair. Now let's say I am these are the outcomes, and what is the game? So let's just write that. So player 1 bets 1 rupee, okay, and 2 bets 3 rupee. Okay. Player 2 bets 3 rupee. Now player 1, so this is the experimental player 1, the context is 1 picks a card at random, and he wins. Sorry. If card is spades, otherwise 2 wins, right? So this is the game. Now to resolve this, we are going to introduce a random variable now, and the random variable is in some way going to measure what is it I want to know. What is how much money do I gain? So I am player 1, let's say, and how much money do I gain by playing this game for a long time? Let's say I'm going to play this game for a long time, and this is kind of what I want to know. How much money am I expected to learn, to gain, or to lose? Okay. And so let's say, so this game, so the random variable, so now random variable, as we said, each different time of the experiment, it's going to return different values. And what is the values? It's going to return 3 if the outcome of the experiment, if outcome is spades. Okay, so the random variable value is 3 if outcome is spades, or -1 if so -1 otherwise. So that's clear why I have this random variable, right? Because I get 3 rupees if spades is what I pick, otherwise I'm going to lose 1 rupee, so it's -1, right? And I am interested in what is called as the expected value of x. and the expected value of x is, okay, so it's three times probability of so this is where we bring in probability and we say that, okay, how many times, what is the probability of me winning spades, getting spades, or the outcome of the experiment being 3, right? So that's what, and that's probability that x is equal to 3, and I'm going to multiply that with, so each time I get I get spades, I'm going to gain 3 rupees, right? And each time I do not get a spade, I'm going to lose 1 rupee. Okay, so that's how this equation comes up, and therefore this is same as, now what is the probability of me getting a spade, and that's going to be 1 by 4, right? So minus 1 by so this is minus 1 into 3 by 4. So what is the probability of not getting a spades? That's 3 by 4. So this minus is 0. Okay, so the expected value is, if I play this game, is 0. So in some sense, what it says is that it does not matter whether I play this game or not, because I'm not going to lose any money in the long run if I play this game. Okay. Here is an exercise for you. It's called as the crown and anchor game. It was pretty much famous among British seamen in 18th century. So seamen are people who kind of work in navy, something like merchants, etc. The game consists of a mat with these 6 symbols. So the symbols are the 4 symbols in a deck of cards, like hearts, diamonds, spades, and clubs, along with 2 additional symbols, which is the crown and anchor. Okay, and that's why the game is called as crown and anchor. Along with this mat, there are 3 6-sided dice. Okay, so 3 dice are there, ordinary dice, and just except for one difference, in that it's not numbers, but each side of the dice consists of one of these 6 symbols. Okay, so a dice will have this hearts, diamonds, spades, anchor, crown, etc. in each of its sides. What a player does is the following. A player is going to bet on one of the 6 symbols. So let's say I am a player, and what I'm going to do is that I'm going to say that I'm going to choose one of the symbols. So let's say I choose spades. I choose spades and I'm going to bet 1 rupee on it. Okay, okay. As an example, I'm going to bet 1 rupee on spades. And then I do my experiment, that is throw the 3 dice. Okay, that's the experiment. And now what is the outcome? So possible outcomes are, one of the if the outcome turns out to be all spades, because I had chosen spade as my symbol, it turns out to be all spades, then I'm going to gain 3 rupees. Okay, so it's a gain of 3 rupees, which means that I get 3 rupees along with the 1 rupee I had placed the bet. Okay, now if only 2 dice show spades, then I'm going to gain 2 rupees along with this 1 rupee which I had placed bet on, and if there's just 1 spade, I'm going to get 1 rupee along with I'm going to gain 1 rupee. Now if there is no spade comes up, I'm going to lose that 1 rupee. So that 1 rupee is taken by the club. Everything is clear. So if in place of 1 rupee I bet x rupees, then if it is 3, if the die shows 3 spades, then I'm going to get 3x times the money I bet. If it shows 2 spades, then I'm going to get 2x times. And if it's just 1 spade, then I'm going to see 1x times the money. Okay. Now if there's no dice, then I'm going to lose the x rupee. I hope just till now it's clear. Now the question is the following. So you have to answer these questions. You have to first write down the random variable for my earning. and then find out its expected value. So what is the expected value of that random earning? So what the random variable? So what does it mean? It's basically that tells me how much money am I going to earn in the long run, right? And do you think I should play this game? It's obviously tied to the expected value. Am I going to gain something, or I'm going to lose something if I play this game? How Cardano approached the problem. So Cardano found out that, see, my chance of winning depends on the number of my outcomes. What is the ratio of outcomes I'm going to get compared to what is the ratio of outcomes you are going to get? And if I'm going to get more outcomes, the game I am highly likely to win. And if you're going to get more outcomes, you are going to win. So that's kind of the idea with which Cardano analyzed games. Now, but he was caught up. He knew there are some issues in the sense that it all depends on whether the game is whether the instruments of the game is fair. For example, it has to be a fair die, meaning there has to be each side. There is equal likelihood for each of the symbols in the die to fall. Right? Do you know of any unfair die in history or mythology? Yeah, so that's the die in Shaguni used in Mahabharata, for example. Okay, so I mean, so people knew about dice which are unfair, and you can construct dice which are unfair, and so that's where Cardano was, and so he also understood. So basically, he understood that there is a cyclic definition. So to define a fair die, he has to use probability, and to define the probability of my success, I have to talk about a fair die. So this is it's kind of caught in this loop, and there's some circular problem there. And on the other hand, these two, Pascal and Fermat, what they did is, so they came up with, so they were interested in solving when a game of chance, like let's say Ludo or something, it stopped midway. How should the proceeds of the game be divided between the different participants? So that was the question Fermat and Pascal had were trying to solve, and they came up with some very nice ideas of random variables and expectation, etc. So that's kind of the status till now. Bernoulli comes into picture. So Bernoulli was he was born in Sweden, and he's a mathematician in 1655. So Bernoulli had a great influence in probability. His work is called Arts of Prediction, which was published after his death, in 8 years after his death in 1713. Okay. So which contains a lot of things which we are going to see now. So when Bernoulli comes into picture, this definition of probability was still not formalized. As we said, it's kind of a cyclic definition. So let's run through it again. What is the current definition of probability? So it's being defined like this. So probability of an event is the proportion of times it occurs in the long run. So you consider an event in the long run and see how many times it occurs, and then that's considered as the probability of that event. So that's the usual definition existed during Bernoulli's time, and that's kind of the definition we all try to understand, right? And intuitively, that's clear. It's a good enough definition. But there are some mathematically there are some issues. So let's see that. Let's consider the issue with this with an example of coin tossing. Okay, and so you have a coin with heads or tails. Now, so let's say I want to say that my coin has a probability of heads is half. Okay, that's what I want to say. Now, according to the definition, how will I say it? So I will say that if I toss the coin for a long time, okay, right? I keep on tossing the coin for a long time, the proportion of heads tends towards half. Okay, this is something I can say. This is what the definition I would like to say. This definition has two problems. One, the sequence of heads I am having can be a all head sequence, which means the limit is 1 and not the half which we wanted to have, right? Because I want to say that the proportion of heads is half, but there are sequences with all head sequence whose limit is 1. Here's another problem. A limit need not exist. So it can happen that after some number of, so initially, so here is an example. So initially 2 heads appear, then 4 heads, 4 tails, then 8 heads, then 16 tails, then 32 heads. So you can see that it's shifting. So initially the when it starts with 2 heads, it's basically all heads. Then you can see that okay, more than half, right? The number of tails is double the number of heads, and then you can see that the number of heads is more than double the number of tails, and so on and so forth. So every time it's doubling and going, right, and it's shifting. So the limit won't exist because it's shifting. It's the once head is more and then tails gets more, and so therefore the limit does not exist in such sequence. So you can construct a lot of sequences where the limit does not exist. So there can be sequences where limit won't be half, and there can be sequences where their limit does not exist. So how do I then say that if I toss the coin for a long time, the proportion of heads tends towards half? Because it all depends on what is the kind of run you are looking at, right? So one can say that okay, these sequences are very unlikely, right? So only consider the likely sequences. But then what is likely here, right? So that again depends on definition of probability. But we started off with the definition of probability, and then we are saying okay, we wanted to define probability, and then we are saying okay, only consider the likely sequences, which means that and what is the meaning of likely sequence? Again, you have to again talk about probability. So again, the cyclic definition we had encountered earlier. This is kind of a situation with which Bernoulli is in. Okay, and now how does Bernoulli solve this problem? So Bernoulli first, so there are 2 ideas of Bernoulli, and the first idea is the following. So Bernoulli said that probability of heads, so probability of any event is going to be a number between 0 and 1. Okay, so probability of heads is a number. Now in this example, probability of heads is a number p between 0 and 1, and you say that a coin is fair if this p is half. Okay, so now probability, we know what's the definition. Probability is just a number. Probability of any event is just a number between 0 and 1. And then you say that a coin is fair. You're going to define the fair coin by saying that its probability is half. Probability of heads is half. Okay. Then Bernoulli went on to prove. So this is his second idea. The first is to say that probability is a number, and the second is he went on to prove what one can say is the fundamental principle of probability theory, which says that, which is called as a law of large numbers. It says that in the long run, okay, in the long run, with the exception of a small fraction of runs, the proportion of heads has a limit which is equal to p. Just think about it. It's saying that if you consider this, you do this coin tosses for a long time. Okay. Now, except for few runs, okay, just some of the runs you remove it, except for some small fraction of the runs, all the other runs is going to tend towards p. This is what is called as a law of large numbers. Okay, this is kind of the idea we wanted, but now because of Bernoulli's first idea of probability being just a number, he can then argue about, he can then show that the law of large numbers. Okay, so this is intuitively this is the law of large numbers, but I'll just write the mathematical statement of this law of large numbers to make it precise. And there are actually 2 laws of large numbers. I'll just talk about the strong law of large numbers, which is saying, so the strong law of large numbers is saying the following. So consider this random variable, which is 1 if head falls and 0 otherwise. Okay. And consider this Sn. What is Sn? Sn is basically you toss the coin n times and take the proportion of, so Sn basically takes the proportion of heads, right? Because x1 is 1 only if it's heads, otherwise it's 0, and x2 is 1 only if it's heads and otherwise it's 0. So how many heads are there in these n tosses? So that by n will be Sn. So it's kind of it's the ratio of proportion of heads in n coin tosses. Okay, so for every run, Sn every run of n length, Sn gives me some ratio, right? Okay, now the strong law of large number says that now you consider this limit as n tends towards infinity, limit Sn is equal to p. That's what we want, right? And but it says that this happens with probability 1. That means, so just think about what it's trying to say. It's trying to say that, okay, you consider any long run. Okay, now it's highly likely that it's going to tend towards p. That long run contains number of hits very close to p. Okay, except for some few runs. Okay, except for some few runs which is not going to be p, which can be somewhere else. Which okay, and now if you keep on increasing this n, this exceptional runs which are not going to tend towards p, this exceptional runs are going to be increasingly getting so the number of exception runs are going to be lesser and lesser as n gets bigger and bigger. So as n grows, the number of exception runs as a fraction of n goes smaller and smaller. Okay, and as n becomes n and n as n tends towards infinity, the number of such exceptional runs tends towards 0. Okay, that means as n tends towards, so that means the probability of Sn as n tends towards infinity, so the probability of limit of Sn as n tends towards infinity is equal to p is equal to 1. Okay, so that means, so you get the idea. So or except, so the number of exception runs are tending towards 0, and almost all runs are tending towards p. That's the strong law of large numbers. Okay, I hope this is clear. Let's go ahead. Now, how did Bernoulli prove this? Now, so this was so Bernoulli used some of the ideas which Pascal already knew and Pascal already have been talking about. And let's start with what is Pascal's idea. So Pascal observed that when a coin is tossed twice, there are 4 outcomes, and he observed that these 4 outcomes, it's very closely related to what we know as binomial coefficient. So in the sense that how many in these 4 outcomes, how many h outcomes are there? That's just 1, which is the coefficient for h square. And how many t outcomes are there? That is the coefficient for t square. How many outcomes are there which has 1 h and 1 t? That is 2, right? That is the number of coefficients for ht, and that's 2. So this is so in some sense the binomial coefficients are closely related to coin tosses, and you can look at 3 coin tosses. So again, how many outcomes are there with 3 h's? Just 1. 3 tails, 1. 2 heads and 1 tail. That is 3. So this one, and this one. So there are 3 outcomes with 2 heads and 1 tail, and 3 outcomes with 1 head and 2 tails. Clear? Okay. And then Pascal constructed this triangle called as Pascal's triangle, and which basically has this outer diagonal. So basically the edges of this triangle to be 1. Okay, except for the base, the other the edges of the triangle is 1. And and for any number, the middle number is got by adding the top 2 numbers. For example, this is 3 because this is 1 plus 2. This is 6 because it's 3 plus 3. This is 6 because 5 plus 1. This is 20 because 10 plus 10. 35 because 15 plus 20. So this is Pascal's triangle. Okay, so that is going. So as you can see, what is this? This is basically the binomial coefficient. So you can see this 1 to 1 is h plus t square. You can see that the first row corresponds to 0, h plus t raised to 0. The second row is h plus t raised to 1, which is 1 1. This is h plus t raised to 2, that is why the coefficients are 1 2 1. Third is h plus t raised to 3, it's 1 3 3 1. And what is h plus t raised to 4? It's 1 4 6 4 1. Okay, so this is Pascal's triangle. now, and these numbers are what are called as binomial coefficients. Now, so binomial coefficients are not something, I mean, Pascal it's kind of known earlier. In fact, binomial coefficients were known long back in China and India, for example, and in India, for example, a mathematician called Pingala had written about binomial coefficients in something like 200 BC. Okay, but those are too old for a recorded data, and I mean, yeah. So Pascal had written this thing in the modern language, which we understand. Okay, so therefore it's now this is a more famous notation. Okay, so this is where we stand now, and then Bernoulli comes in. And he says he observed the following. So consider a coin with probability of heads p, and then Bernoulli observed the following, that okay, I want to answer this question: what is the probability of k heads in n coin tosses? Okay, and so Bernoulli observed that that's equal to the term n choose k with p raised to k 1 minus p n minus k. This is the probability of k heads in n coins. So this is what Bernoulli observed, right? So if someone asks what is the probability of something which we can just now check, what is the probability of 2 heads in 2 tosses, 2 coin tosses for a fair coin? So that is n is 2, k is 2, 2 choose 2, 1. This is half, right? So it's right. So this is half, and this is I mean, k is 2, so 1 by 4. So we know there are 4 outcomes, and it's 1 by 4. 2 heads is 1 by 4. Okay, and you can check for other answers too. So this is what Bernoulli observed first, and he's going to use this idea to show to argue his law of large numbers. And so let's see. So let's assume a fair coin, and we're going to see an example. Now consider 3 coin tosses. Okay, and I'm going to remove. So what is the law of large number? It says that in the long run, if you remove some exceptional runs, the proportion of heads has a limit which is equal to p. So you have to show that if you remove the some fraction of runs, the rest of the runs are going to tend towards p. Okay, this is what you have to show. And so we are going to remove the extreme case of 3 heads and 3 tails. And what are the other kinds of runs? The other kinds of runs has either 2 heads or 1 head. So the ratio of heads in the other runs is 1/3 or 2/3. So that's kind of between, that's sandwiching. This 1/3 and 2/3 is sandwiching between p, right? So you can see that already you have shown with just 3, n is equal to 3, you have now kind of shown that p is between these two numbers. This is something you can take it as an exercise and try to consider n is equal to 4 and remove the extreme cases and see how many I mean, how close are you getting towards p. Okay, so yeah, so as the length of run increases, the proportion you get closer and closer towards p. So that's kind of the argument for Bernoulli. And then you're closing in towards p from both directions, and that's basically the idea of Bernoulli. Okay, now yeah, so this he generalized and proved the law of large numbers in general. Good. Now here is an exercise. So consider this figure. It is an 1 cross 1 square. Okay. Now, and there's a circle enclosed inside. So what you should do is you write a computer program to randomly pick points inside the square. Okay, and then find out how many of those points are inside the circle. So you can find out that ratio. So let's say you pick 100 points and then find out how many of those 100 points are going to fall inside the circle. Next, you can increase the number of random points, take some 1000 random points and see how many of it are inside the circle. Where do you think this ratio is tending towards? Any idea? So this is that's kind of that's what you can try with experiment with some computer and see where this is tending towards, and then you should also try to think where it's going towards. So next we move on to conditional probability. So where are we right now? So we have now seen that Bernoulli has come up with a better definition of probability, which is now not cyclic in nature. But let's go back to Pascal and Fermat for a moment. So along with so we are told that Pascal and Fermat had come up with the ideas of random variables and expectation. So along with that, they also came up with the idea of conditional probability. And why is it that they have to think about this problem? So because they have, as we know, they have been working on how to divide the the stakes among in an incomplete game. That's what they have been interested in, and this is typically a question which arises there. What is the probability that uh, A A is a person? So what is the probability that A is winning the next round, given that A won last 5 rounds? So that's kind of so this is the that's kind of a question which they have to think about, right? Now, so this is called as conditional probability. If you know that A won the last 5 rounds, can you tell what is the probability of him or her winning the next round? So, so this is how you write. So, what is probability of A given B? Probability of A given B is probability of A intersection B by probability of B. This is straightforward. You can see it from set theory. So probability of A intersection B by probability of B. You can rewrite it by saying that, okay, you can take probability of B on the left side, and then it becomes probability of A intersection B is equal to probability of A given B into probability of B. Right. We also say that this is particularly important, what's called as independent sets. Two events are independent if probability of A intersection B is equal to probability of A into probability of B. So, so in a sense, what does it mean? It means that you cannot distinguish. So given B, that does not, so knowing the information of B does not help me in any way. It's not going to help me in understanding what is going to be the probability of probability of A. Okay, so that's independence means. Okay, so knowing B does not help me to know A better, right? So we are as much clueless as we were before. Okay, so that is that's called as independence. So for example, if you're like, let's say you have a coin, you tossed 100 times, and you're going to toss the coin 101 times. It does not. So the what is what is the probability of the coin getting heads? It does not depend on what happened in the past 100 rounds, right? It's exactly the probability of the coin toss getting a head, right? It does not depend on what happened in the past. Okay, so then so the two events, the event on the 100th toss and all the rest of the 99 toss events, they are independent. Okay. Yeah, so as an exercise, if you don't know this problem, so try to look up this problem, what is called as a Monty Hall problem. Just check it out, in Wikipedia or YouTube, anywhere. First see the question, try to think about the solution. Okay, and don't worry if you have not seen it, it's very difficult to come up with the right answer. I mean, you can try to guess what is the correct answer, but to solve it might take some time. So you can spend some time, or even if you don't get, do not worry, you can read it up. Okay, so that's the Monty Hall problem, and Now, the conditional probability is kind of very closely related to what is called as Bayes theorem. Okay, so first of all, let's look at what Thomas Bayes was looking at. So Thomas Bayes in 1700 had the following question. So what is the probability of something happening in the future if I know how many times it occurred or not occurred in the past? So if I know something of the past, can I predict something in the future? You know what, this is something like a machine learning kind of question. In fact, Bayes theorem, Bayes rule, etc. is a big area in machine learning as such. So you can see it's like a machine learning question. Can you predict what is going to happen? Now, so in some sense, so this is what in Bayes theorem informally you can state it as, if you have some initial beliefs, initial knowledge, and plus some recent observation, then you have an improved belief. That's kind of thing Thomas Bayes is trying to achieve. Now, even though he did not successfully answer the question, after his death, his friend Richard Price modified and corrected the notes of Bayes and got it published. And so it comes up with, and here is the Bayes theorem. So which says that, so probability of A given B is equal to probability of B given A into probability of A by probability of B. So, I mean, now you know that because, why do we know this? Because you know that probability of A given B into probability of B is equal to probability of A intersection B. And probability of B intersection A is same as probability of A intersection B, and probability of B intersection A is probability of B given A into probability of A, right? So you can see it that way, and you can rewrite probability of B by the following. So what is probability of B? So you can replace probability of B by saying that, so probability of B is probability of B intersection A plus probability of B intersection A complement, right? So this A with a bar on top is A complement. So probability of B intersection A plus probability of B intersection A complement. That's probability of B, and that's what. So that's probability of A given B, and this is Bayes theorem. And how do we use it? Let's see an example. So there are two coins inside a bag. One is a fair coin, and the other has two heads. So it's like the Cholet coin, okay, which has two heads on both sides, or was it tails? Okay, let's assume the Cholet coin had two heads on both sides, and so we have a fair coin and the Cholet coin. Now, I mean, those who don't know Cholet was it's a famous Hindi movie acted by Amitabh Bachchan, where Bachchan had a coin with heads on both sides. Okay, he uses that to, I mean, take advantage of some certain situations. Okay, now, so we had two coins, one a fair coin and the other is a Cholet coin, and we pick one of the coins at random. And we tossed 10 times. All the tosses came out to be head. What is the probability that the coin we picked was a two-headed coin? Right? How do we answer this? Bayes theorem. Let's see. So we know Bayes theorem. So let's try to push in A and B. What is A? A is the event of picking a two-headed coin. So A complement is the event picking the fair coin, and B is the event of 10 consecutive heads. Okay. Now, what is probability of A? It's half, because I could have just picking one of these coins at random gives me half probability for picking either the fair coin or the Cholet coin. Okay. Now, what is probability of B given A? So probability of B given A. So if I had picked the Cholet coin, I picked the Cholet coin. What is What is the probability that I'm going to get 10 consecutive heads? You're always going to get 10 consecutive heads because you have the coin has heads on both sides, so you're going to get 10 consecutive heads for sure. So probability of B given A is 1. And what is the probability of B given A complement? So probability of B given A complement is you had picked the fair coin and you have a situation where you have picked 10 consecutive heads. So that means all are heads, and so at every time you have a chance of picking the heads with half probability. So it's half product of half 10 times, and it becomes 1 by 2 raised to 10. Okay. So this is so I have probability of A, B given A, and probability of B given A complement. So now I can answer this, fix this, fill in the blanks now. What is probability of A given B? Is that what we are interested in? We are interested in if I know that the event of 10 consecutive head has occurred, what is the probability that I had picked up the two-headed coin? That's what we are interested in. So we are interested in probability of A given B, and I know B given A and everything else, so I can just fill in that, and if I fill in that, I'm going to get this. You can just check the calculation. So so this is like 1024 by 1025, very close to 1. So if this had happened, you can say with very high confidence that you have picked a two-headed coin. You have picked the two-headed coin. That's what Bayes' theorem tells us. Now, here is an exercise. It's an application of Bayes' theorem. Can be used in medicine. Consider a disease which affects 1 in 10,000 people. Okay. So a blood test can detect whether you have the disease or not. However, the test has a small false negative rate. That is, a person with the disease might test negative. So you have a disease, but when you do the test shows negative. And so this can happen in 1 in 1,000. The test also has a false positive rate of 5%. That means 5 in 100 people or 1 in 20 people who do not have this disease might also be tested for positive. Okay, so he or she may not have the disease, but the test will show that you have the disease. So that is false positive. Okay, now your positive result is false. Now assume that a blood test shows that you are positive. What is the probability that you have the disease? Right. So you have to. What is it you have to answer? Sorry. Now what is it you have to answer? You have to answer the following questions. What is A? Right. You have what is B, because you need to use the Bayes theorem. What is A? What is B? And what is B given A, B given A complement, etc. So try to find out the answers to all those things, and then find out probability of A given B. This concludes our topics on discrete probability, and we move on to continuous probability. So before that, I just want to share a few exercise questions which you should try to solve. First is commonly called as a birthday paradox. So here is an exercise. So a room contains 40 people. What is the probability that at least 2 of them will celebrate the birthday on the same day? So there are like 40 people there, and you can assume that no one has a birthday on February 29th. So just 365 days, every person is going to have a birthday on one of the 365 days. Assume it's equal probability for everyone to have a birthday on a particular day. Now in this scenario, if there are 40 people, what is the probability that at least 2 of them share their birthday? Now once you do this, you can try for say the number 23. So that is, if the room contains 23 people, what is the probability you see? Try it for 100. So this is birthday paradox. Next question is called as the coupon collectors problem, but I am giving you a simplified version of it. So there is your popular chocolate brand. I'm going to call it X. Okay, so each time you buy a chocolate, you're going to get exactly one of the card symbol. So you're going to get a card with one of the symbols, either hearts, diamonds, spades, or clubs. Okay, so every packet you buy, you're going to get one, exactly one, right? And it can happen, any of these symbols can appear with same probability. Now, so what is your aim? Your aim is to collect all 4 symbols. So you just go and keep on buying packets of chocolates until you get all 4 symbols. So if you collect all 4 symbols, you can go to the company and then you can get some gift. Now the question is, in expectation, how many packets should you buy to get all 4 symbols? Right? Assume that a packet is equally likely to have, so that's the assumption which I already told that. You can assume that any of the 4 symbols is equally likely to appear in a packet. To solve this problem, you have to use what is called as linearity of expectation. So it says that if you are given 2 random variables, x1 and x2, it can be any kind of random variables. The expectation of x1 plus x2 is equal to expectation of x1 plus expectation of x2. So this is called as linearity of expectation, and this it's not. You can even extend this to any finite number of random variables. So you can consider random variables x1 to x1, x2 up to x5, let's say. Then expectation of x1 plus x2 plus up to x5 is equal to expectation of x1 plus expectation of x2 plus up to expectation of x5. In fact, it's even more stronger. So it's called as linearity of expectation. So if you know some linear transformation, so it's basically talking about if you expectation of a x1 plus b x2 is equal to a times expectation of x1 plus b times expectation of x2. So that's why it's called as linearity of expectation. Now you'll have to use this this property of expectations to solve this coupon collectors problem, and even otherwise this is a very important theorem to know, the fact that expectation satisfies this condition. It's going to be useful in many going to help you in solving many problems. Now finally I have what I can say is a trick question. So here's a question. So I do not have a fair coin. Now I want to use that coin to decide who will bat first in a game of cricket. So because you want to start the game of cricket by tossing a coin and the winner deciding whether to bat or bowl, right? So I want to convert. But the coin I have is not a fair coin. So I want to convert the coin into a fair one. Note that I do not even know the probability of the fairness of this coin. I do not even know what is the probability of the heads coming. Okay, so in this situation, how can I use that coin to use it use it for a coin toss in a game of cricket? Right? This is a trick question. So so you can try to think how to do this. Finally, 4 is this question: what is the probability of getting 50 hits when tossing 100 fair coins? So you're going to toss 100 coins. They are all fair. And what is the probability that you get 50 hits? You know the answer. You know how to solve this, because it involves binomial numbers, which we have already seen. But the numbers are very big. So can you come up with an answer to this question? Right.